Hi engineers, and welcome to 2.1.3, which is called free body diagrams. Today we're going to learn about free body diagrams, what they are, how they're useful to us in the engineering world, and how to set them up. There are different forces involved in a free body diagram. Let's get started. So I just went over to Google and I typed in free body diagram in the image search. And what free body diagrams are, if you've taken physics, we use them pretty extensively first semester. What they are is just a picture of an object with the forces acting on them. So here's a really simple one. Here's a box. It's resting on the ground, so it has weight. There's a force down of weight, and you're always going to have that force. Now, since this box is resting on the ground, the ground is providing an upward force, and that's being pushed on by another force. Here's another one. They call this the normal force, the upward force provided by the surface. Force of gravity. There's an applied force, but in this case, there's friction. Here's what we call a inclined plane. You'll still see that normal force, that force that's perpendicular to the surface. You still have gravity pulling straight down, but now friction's at an angle. Just some other. Here's a kind of an interesting setup where there's a roller here and then like a pin. And you're pushing on it with a force of 390, and there's some sort of torque of 800 foot-pounds. There's a person resting on a ladder. You'll see here's the weight of the ladder. Here's the weight of the person. The wall is pushing against this. And then the ground is pushing up, and then the friction is keeping it from sliding out. So free body diagrams, they're just pictures that have arrows that kind of represent how much force is being applied to an object. It's a picture of force and its interactions, or a diagram, you could say it. Individual objects are separated from their system, illustrating all forces. So here's a pulley. We're going to start looking at trusses. Like if you've got a bridge, we're going to look at one specific joint right here. And so we'll take this joint and we'll look at the forces acting on that specific joint. Or here's a beam, and you've got this is a pin over here, and here's a roller. So we're looking at, looks like there's two loads on this thing. So we're looking at the forces on an object. So a force, we talked about forces before. It's a vector quantity, or it's a push or a pull, acting upon an object. A vector quantity, remember, it's got two things. It's got a magnitude, how big, and it's got a direction. And you can tell how big by the length of the arrow, and you can tell what direction by the angle, the direction that the arrow is pointing. So arrows are really helpful when describing forces because they tell us how big and in what direction by the size and the direction that they're pointing. A free body diagram. So this is what we call a moment or a torque. Torques we show by arrows going in a circle. They can be counterclockwise, which we say are negative, and so sometimes we'll use blue. And they could be clockwise, which are the positive direction, and we'll use red to kind of help ourselves keep them track of each other. They're an arc that shows the direction of rotation. The arrowhead indicates what direction it's rotating. Remember that torque is equal to your force times your distance. So this right here would be a positive torque because you're pushing up with this force, so you're trying to rotate it counterclockwise, which would be a positive moment. Free body diagram. So how do you actually make a free body diagram? Here's an example. It says you got 3 books stacked on top of each other. Intro to Engineering Design, Principles of Engineering, and I forget, Design Engineering. So it says create a free body diagram for the top book. So here's the top book. So what we're going to do, we're going to draw the top book. And there's a force. And this force is always present. It's the force of gravity. I don't know how much the book weighs. Maybe it's 1 pound. Maybe it's 2 pounds. Maybe it's 3 pounds. And then there's a supporting force preventing that from going all the way to the center of the earth. We call that the normal. And in this case, since the book is still, it's in equilibrium. The normal force in this case would be 3 pounds. So here would be a very simple, very basic free body diagram of a book. You've got a downward force of gravity, and then you've got an upward force provided by the ground supporting it. Here's one for a sledder. You're pulling on some sled. So remember, the one force that's always present is gravity. Maybe these kids weigh together, plus the sled, 100 pounds. I don't know. You're pulling it, so we're going to go like this. Force of a pull. Now, if there's ever a rope, the rope pulls in the direction of the rope. So if that rope was at a different angle, you'd make your arrow at a different angle. There is a force provided by the ground, the normal. And I'm assuming there's a little bit of friction. So now we're getting into another type of force. Friction. Friction is going to always oppose your motion. So here's a free body diagram of this sled. I'm pulling it, there's friction, gravity's pulling it down, and then there's a normal force. A refrigerator being pushed up an inclined plane. You always have gravity. Maybe this refrigerator weighs 200 pounds. I'm not sure. This person is pushing on it. So a lot of people, you think that you do this, that you apply your force of a push in that direction. The common way to do free body diagrams is you always put your arrow moving from your object. So that force over here, the force of my push, let's put it over there so that it's going from our object. There is a normal force, and the normal force is always perpendicular from the surface. And there's friction in this case too. Friction is preventing me from going up that angle. So here's a free body diagram of somebody pushing something up an incline. Create a free body diagram for the pulley system below. So create one of mass 1. So I'm going to take mass number 1. We'll make a picture and I'll label it M1. The force is acting on M1. There's gravity, the one force that you'll always have. And now you'll see that there's a rope right here. And we'll call that the force of the rope. And remember I talked to you about how ropes are always acting in the direction of the rope. And since this rope is pulling straight up, that's the way the force is acting. So here's a free body diagram of mass number 1. Make a free body diagram of the movable pulley. So here what I'm going to do, I've got my movable pulley. This mass is pulling me down. So I'm going to go force of gravity of mass number 2. Just to be a little bit more, so you don't have to do that, but box number 2 here, mass number 2 is pulling me down. And I've got 2 forces lifting me up. So I've got a force over here, this string. Sometimes people label that as tension, force of tension. And there's another one. There are 2 ropes lifting up on that pulley. And just for, I mean, if this was, let's say that mass 2 was 10 pounds, that means that this is 5 pounds and this is 5. That's kind of how that works. That's how pulleys get away with doing what they do. Different types of support reactions. We can have cables, which you've seen me use already, so, a rope pulling on something. We can have a pin, a roller, or a built-in cantilever. And I'll tell you more about specifically each one of these. When we make a pin, we do a pin with a little triangle. So, and sometimes you'll see inside of a free body diagram a little triangle. A roller looks like a circle, and then a cantilever, you'll have like a wall and something cantilevering out. And I'll explain more about those here to come, but that's kind of what they look like. Here's an example of a cable. So here's my, if I was going to make a free body diagram of that weight, I would have the force of gravity, and then you replace the cable with only one force, and you can label it tension, you can label it rope, you can label it cable, you can label it whatever you want. So you replace it with a single force acting in the direction of the rope. Here's a sign, and it's got two ropes, so there's going to be a force here. We'll call it number 1, and then there's going to be a force here. We'll call it number 2. They don't have to be equal. One of these could be pulling harder than the other, and that's probably what's going to be happening. But you just replace those, and then I would put gravity in here, which is pulling down on our sign. A pin. So here's an example of a pin, and you see it right here as a triangle. A pin is replaced with two forces. You're going to replace that pin with two forces, one in the X direction and one in the Y. If you pin something, imagine like if I took a pin to a bulletin board, that thing can't move up and down, nor can it move left and right. So what we do is we're going to label this one the force at A in the Y direction, because Y goes up and down, and this is the force at A in the X direction, because X goes left and right. So every time you have a pin, what you're going to do is you're going to replace it with two forces. Remember, when we have a cable, you replace it with one force in the direction of the rope. If you've got a pin, you're going to replace it with two forces, one up and down and one left and right. A roller. A roller is replaced with one force, and it's in the vertical direction, in the Y direction. Imagine a roller right here. This could roll, so it lets the object move left and right, but it doesn't allow it supports it, so it doesn't let it go up and down. So this roller only supports force at A in the Y direction. So a roller you replace with one force because it's supporting. A pin you replace with two forces because it's both supporting and keeping it from going left and right. So when you have a beam, and you'll notice over here we've got a pin, and over here we've got a roller, we call this simply supported. It's simply supported because that's the least amount of forces that it takes to keep this thing still. Like if you push down on this with 100 pounds, and remember, if it's right in the middle, like so there's an upward force at A, because this is a pin, and there's a force at A in the X direction, and in the B, there's a force at B in the Y. If this is exactly in the middle, each of these things is going to be 50 pounds. And if there's no other forces pulling left and right, this thing right here is equal to 0. So this is the simplest way. We call it simply supported. The minimum amount of forces that it takes to support an object when it's in equilibrium. Sometimes you have what's called a cantilever. And a cantilever you're going to replace with three things. You're going to replace it with two forces. One X and one Y, and you're going to replace it with a moment. So this wall right here at A, if you have a cantilever, there's a supporting force and there's a force keeping this thing from pulling out. And there's a moment. I'll make it red. The moment at A, like that. So there are three things that you would replace a cantilever with. A moment and two forces. One up and down, one left and right. For instance, let's say this was 100 pounds. And let's say this was 2 feet. So RA in the Y, that has to be 100 pounds. Because if this is pushing down at 100 pounds, this has to counter that and push up at 100 pounds. Since there's nothing pushing to the left or the right, this reaction force at A in the X direction, that's going to be equal to 0. And then my moment, this is, you take the torque, the force times the distance. That's 200 foot-pounds. So this is creating 200 foot-pounds in the negative or clockwise direction. So this reaction over here has to be 200 foot-pounds in the positive direction or counterclockwise to oppose that. So these are the three reactions if you loaded this beam as such. If you're pushing down with 100, then this has to counter the upward 100 pounds. Since it's torquing it as well, it has to counter the torque. It's not pulling anything to the right, so then this doesn't have to do anything either. So this is kind of how this all kind of play together when you start loading a beam. So to summarize our different reactions, like if you push, then you put it with one force. If there's a cable, you replace it with one force. A pin, two forces. A roller, one up and down. And if you have a cantilever, you've got an up and down, left and right, two, and a moment. So when we get into more complicated objects, like a bridge, it says draw a free body diagram of the entire bridge. So what you're going to end up doing is looking at each one of these things individually. So here's point C. Since there's a roller, the roller only provides a lifting force. So you'd say the force at C in the Y direction. Now, there are two forces. There's one here and one here. So you'd say the force, and this, we'll call this CD. And we'll call this CB. Like that. We'll go over here to this joint, point A. Now remember, there's a pin, so there are two forces that this has. There's a supporting force and there's one left and right. And again, I've got two forces here, FAE and then FAB. A very subtle difference. You know, I've got two reaction forces here, right? I've got a reaction force in the Y direction, and I've got a reaction force in the X direction. But over here with my roller, I only have one there. If I would do this spot right here, here's point B. There's a 500 pounds down. Now I've got this force, this force, this force, and this force. Whew! BA. And this is BE. This is BD. And this is BC. Here's this one, point D. There are three forces. And this is DC. And this is going to be DB. And there's this one, DE. And where we're going with this, I'm going to skip over and not do this one just because we're kind of, I'm getting to the point of as long as I want to talk to you. Where we're going is that once you find this force, you can come down here and know this force. Like, we're going to end up solving for all of these forces through a little bit of what are called identities. That, like, this force is the same as that one. Those of you in physics, you might, a little preview, because there's an upward force, the component, when we break these into components, the y component, this y component is equal to that. And then you can use sine and cosine to find this right here. And then you know that. And then everything kind of falls out afterwards. But suffice to say, free body diagrams. Forces on an object that are provided by pushing or pulling and with an arrow.